Hello, welcome back. So in the second section, so we will discuss the sub areas of AIOps research. Okay. Um, so first, so we know that AIOps is AIOps is most about leveraging artificial intelligence to analyze and monitoring data, right? And to use this analysis of monitoring data to support IT operations. Okay. Um, so AIOps research areas usually can be divided into two main directions. The first direction is about how to produce the monitoring data. That is how to use the monitoring code to produce monitoring data. The second area direction is about how to leverage the monitoring data, how to analyze the monitoring data. Right. So we call them monitoring code made right and monitoring data used right. Okay. So we'll see the concrete sub areas in next slide. Okay. Okay. So the first subtopic is autonomous configuration. So this is about how to automatically configuring the software system based on monitoring data. So we already discussed about this topic in our motivating example. Okay. Then we have a log abstraction. This is about log parsing, how to pass unstructured log data into structured log data. So we will see an example later. There's a fault diagnostics. Okay, you use the monitoring data to debug the system, to find the root causes to the failures. Okay, for fault diagnostics. Next, anomaly detection is about to detect whether there's a problem and maybe where is the problem. Okay. Performance analysis to analyze the performance of the system. Incident prediction to predict future incidents. Okay. System comprehension to leverage the monitoring data to understand the behavior of the system, to understand what is expected, right? So we know when there's something unexpected, we know there's something wrong. Okay. Next is AIOps infrastructures, and is to support the various AIOps topics. Okay, and also we have a logging practice and automated logging. So these are about how to generate monitoring data efficiently. Okay, especially here you focus on logging because the logging is one of the most important source of monitoring data. Okay. So there are many subtopics. So here I will go through some of them and give you a sense of what are the topics of AIOps research. Okay, the first, let's look at log abstraction. Okay. So in the previous lecture, we discussed how to generate logs, right? How to produce logs. We insert logging statements in the source code to generate logs, right? So during software execution, the software system would generate a large amount of log data. Okay, so this log data is so large that it's beyond our human capacity to manually look at it, right? So can we, this is something here. Yeah, so here, for example, these are the several lines, 4 lines of log data, right? If you look at these 4 lines, right, we can see that there are some templates, right? There's some static information, some dynamic information. For example, user checkout for account ID Tom item equals to 100, and the user checkout for account ID Jenny item equals to 100. So here, Tom and Jenny, so they are dynamic values, right? The change, but the properties are produced by the same logging statement, but they have different variable values. Okay, if we can if we can find the template, so we can convert the line 1 and line 2 into one line, right? So they are the same, they just have a different variable values, right? So log abstraction is about to abstract the log lines into fewer execution events. So the log line 1, log line 2, they have the same execution event, right? Let's see how it works. If you look at this table, actually we only have 2 log events here. First event is user checkout for account at a variable value, item equals to a variable value. So it is associated with the log lines 1, 2, and 4. Okay. And the second log event is item shipped for account ID, item equals to a variable value. It is associated with line 3. Okay. So this is a task of log abstraction. So the goal is to abstract the large number of log lines into a fewer execution events, so you can make our log analysis easier. We can only look at a fewer number of executing events, right? So let's see its application in a large-scale software system at BlackBerry. Okay. So one enterprise application from BlackBerry generates 1.6 million log lines in 8 hours. And 23,000 lines contains the keywords fill or finer. So if you want to look at this log lines and you want to see if there are problems and what are the problems, you need to go through so many log lines, like more than 23,000 lines that contain the fill or finer keywords, right? If we apply log abstraction, so we can reduce the 1.6 million log lines into 319 execution events. Among these events, only 16 contains fill or filler. So if you want to look at the log lines, including fill and filler, you only need to look at 16 log lines, 16 log events. Okay, right? And even better, so you can account for each log event how many times it occurred, and you can focus on the most occurring log event first, right? And you can address the most important problems first. Okay. So this is an example of how to apply techniques like AI techniques. Here I didn't mention the details of the problem, the detailed solutions. There are many solutions, many techniques that can use. You can use machine learning based. You can use other approaches to. You can use heuristics to solve this problem, right? The second sub area is fault diagnostics. This is about to find problems in the system. Okay, let's look at one application. Okay, so we know in this application, so we want to diagnose some memory-related problems like memory leaks. So how to identify memory leaks? So from the system, we have data such as logs and counters. Counters are metrics you can consider here, like so memory usage, how much memory is used, right? So we have this data, we have the logs, and we have the memory usage data, counters. All right, so they are separate, they are stored in separate files. Okay, the first step, what I can do is, so we associate these logs and counters because they have different timestamps. So we need to associate them together. So we need to understand in each time period, what are the logs and what are the counters, right? The logs stores the runtime activities of our system. The counter store the memory usage of the system. After we associate them together, so then we can create a time slice profiles. So for each time slice, we have the log activity and the memory. Especially, we can calculate the memory delta. So the memory data is the difference between the memory from one time slice to the previous time slice. Okay, so we create these time slice profiles. For each profile, we have a log activity, we have the memory delta. Okay, so these are the signatures. Then, so we want to analyze the data. So there are so many time slices. So which time slice I should focus first? Okay. In order to reduce the manual effort, what we can do is we cluster the time slices into groups. So where a similar set of events have occurred, right? For each group, so we have so many time slices. We cluster them into a smaller number of groups within each group. So these node activities, they are similar. Okay. So then we analyze the clusters with the highest memory deltas, right? If a cluster of the time slices have the highest memory delta, then we just need to focus on this group, this cluster first. This cluster is probably associated with the memory leaks or like memory issues. Okay, so this is another way of how we use AIOps solution to diagnose system issues. Okay. The third example I want to show is anomaly detection. Anomaly detection is to find whether there's a problem here in a system. So we have imagine that we have a sequence of log events, right? So here you see three sequences of log events, right? And we find that E2 and E3 always together, right? There are many events of the season occurring always together. Like after you acquire a lock, you need to release a lock. You open inbox, then you close the inbox. So these are things that always occur together, right? And then if we find that in another sequence, E2 is followed by E6, but every other places E2 is followed by E3. So there might be a problem, right? This is a rare case and may indicate a problem. So this is about the idea of anomaly detection. So identify the cases that are irregular. So this might be problems. Okay. So how to identify this irregularity? So we can use different approaches, different machine learning approaches. So one way is, so later on we will discuss some of the common techniques used in AIOps. But here, for example, you can use frequent Python mining, right? Or associated rule mining here. So how this can be applied in a real system, right? So you can see this, there's a case study on Dell DVD store. This is a web service for selling DVDs. Okay, we see that for 98% of cases, E13 is followed by E14. So the event of E13 is followed by E14. But for a very small, less than 1% of cases, E3 is followed by E13, or E13 is followed by E13, or E13 is followed by E15. So these are rare cases. They might be problems. Okay. So using this automated solution, so we can reduce 99.99% of the log lines that need to be examined. So we only examine these irregular log lines, and we can identify the problems with a high precision, up to 100%. Okay. So this is another application of AIOps, right? About anomaly detection. Then I'll give an example of incident prediction. Incident prediction is about predicting future incidents. For example, predicting future failures. So in this example, so we want to predict whether a node of a cloud computer system would fail in the future. For example, in the next day, right? Can we do this? How can we do this, right? There are some monitoring data, some signals that can indicate future failures. They may, so this monitored data, they may have different distributions on field machines and normal machines. Then we can use this data to do the prediction, right? For example, if you look at this figure, we can see that the distribution of the alerts is a type of monitoring data. The distribution of the alerts in field and normal nodes, they are different. They have different distributions. So you can leverage such distribution to predict whether your node will fail or not in the future. Okay, how it works, how can we do it? So first, for each node in a large-scale cloud computing system, so we can connect the data associated with this node and can connect different types of data, include alert data, right? And the spatial data and build data. Alert data are about the alerts of the node. For example, so when there are a certain amount of errors in the system, there will be an alert. This alert will be sent to the operators. Okay. Spatial data is about the location of the machine, right? So which stack, which room is the machine located in. Build data about the configuration of the machine, the memory size, the CPU, and the operating system version, right? Connect all the data together. Then this data will be combined together into the features of a prediction model. And based on the features, so we build a machine learning model. We do hyperparameter tuning, we do data sampling as well. The data sampling is about how to sample the positive and negative cases from the feature data. Okay, so then we evaluate this model on future data, right? On the data set that is connected later than the data used for the training process. So then we see the prediction results. So we find that this this model can achieve an AUC of 0.92. So what is AUC, right? AUC is a popular use of feature to evaluate the performance of a machine learning model. So AUC ranges from 0 to 1. The higher the better. If the AUC is closer to 1, it means the model is better. Okay, so here AUC is 0.92, which is very high AUC. So we can accurately predict whether a machine will fail in the future, right? If we can do this, then operators, it can take some mitigation actions. For example, they can migrate the services on this machine to another machine, right? So this is incident prediction. This is application. Okay. Next, so we will see an example of automated logging, right? So all these previous examples about monitoring data use right? So how to generate this monitoring data efficiently in the first place, right? For example, where should I put logging statements in the source code? I remember from last lecture, developers use logs to record important runtime information, right? So here we show an example of a logging statement. So in order to get enough information from the runtime system, so we need to put as many logging statements as possible, right? But if you put too many logging statements, so there will be significant performance overhead, right? In fact, neither too much nor too little logging is desirable. So we need to optimize the amount of logging in the source code. How can we do it? Can we do it automatically, right? How to determine where to log? How to determine which code snippet needs a logging statement? So this is a problem. So we transfer this into a classification problem. We want to determine whether a code snippet needs a logging statement. How to do it? So we need to get information from code snippet. We need to get features from the code snippet, right? So from code snippet, we can get two types of information. One, structure information, like control flow statements such as if, else, try, catch, those statements, right? Structure information. And we can get topic information, such as, so what is this code snippet about? Here we can see this code snippet is about connection, queue connection. So this is topic information, right? So here I don't go to the details about how we get this information. You can get it. This is structural, this is semantic or topic information, two types of information. So we use static code analysis to get a structure information, topic modeling to get a topic information. This is a very high level explanation. Okay. Then we combine the structure information and topic information into a feature set. And we use these features to explain where to log. We explain which code snippet would need a logging statement. So to do this, so we build a machine learning model. Here we use a lasso model. Lasso, you can consider is a enhanced version of logistic regression. With a lasso model, we build this model using the features from the structure information and the topic information. We build a model to predict whether code snippet would need a logging statement, right? So this model achieves an AUC of 0.87 to 0.99. It's very high AUC. Okay. So here I introduce some examples of AIOps solutions, AIOps sub areas, right? So here in this page, so there are the papers about each sub area of AIOps. Okay, so you can, if you are interested, so you can look at the papers to know the more details about the sub areas. For each sub area, I give one example here. Okay, so that is about the sub areas of AIOps. So here I want to do two small exercises. Okay. In the first exercise, in this exercise, I want you to select the AIOps solutions for given scenarios. It's a very high level practices. Okay. The first one, so giving the monitoring data of large scale software system. So you want to determine whether there's a runtime failure in the production environment. This is a scenario, right? So you want to determine whether there's a runtime failure in the production environment. Which type of AIOps solution will you use? Option A is a fault diagnostics. Option B is anomaly detection. Option 3 is incident prediction. So I want you to choose the one from the three options. Yeah, I want to see the distributions. So I would ask you to go to menti.com and use the code or give the code. Okay. 1 second. Okay. Can you see the uh, so the shared browser?